Good morning, friends. I am Chetan Dhareya, Assistant Professor at SMC College of Basic Science and one of the content writers for Paper 12, Module 27, Packaging of Microwaveable and Irradiated Foods. In this module, we will discuss about different packaging materials which can be used in the microwave packed foods and which can be heat treated at a higher temperature and can survive microwave temperature. The story of microwave oven begins in Britain in 1940 when two scientists working at Birmingham University, namely Professors Rundle and Booth, devised an electronic tube which they called as cavity magnetron that generated large amount of microwave energy very efficiently. The unique ability of the magnetron to transmit microwaves at very high power enabled radar equipment to be built that was much smaller, more powerful and more accurate than anything previously designed. Now in the decade of 1980, there was prolific growth of the consumer microwave oven resulting in a new category of food products. Development of the new products spawned a new market for packaging materials, some of which were capable of being rethermalized in a conventional oven as well as the microwave oven, known as microwavable products and materials. While still other new products and their packages evolved that were developed strictly for heating in the microwave oven. The penetration of microwave ovens into US homes and lifestyle grew rapidly from a mere 15% of the households owning a microwave oven in 1980 to an impressive 78% by 1989. The new category was supported by microwave popcorn, a product that was developed specifically for preparation into the microwave oven. The standard was now set for other new food products that attempted to cater the consumer's desires for foods offering quickness and convenience in their preparation. In the mid 1980s, a wave of premium priced frozen dinners had been witnessed, positioned a higher quality TV dinner that are now available on Thermoset Polyester plates capable of being heated in the conventional oven environment or the microwave. Now to make an microwavable packaging material, the paperboard is coated generally with a fine clay on one side to impart higher surface gloss and proper surface for printing, along with an extrusion coating of a film made of polyester, in some cases for methyl pentane 1 polymer, that is also called as TPX. The thin layer of a high temperature plastic provides a relatively inexpensive method to produce containers that capitalize on the structural strength and economic of the paperboard component while adding the barrier required to keep fats and moisture in the food from entering the paperboard. Other plastics are also extrusion coated onto paperboard, notably low density polyethylene and polypropylene. However, the maximum temperature resistance of LDPE is to 15 degrees Celsius and polypropylene to 60 degrees Celsius. The upper temperature limit for LDPE and PP coated paperboard will dictate the packaging application with a maximum temperature limit of 215 degrees Fahrenheit for LDPE coated paperboard, which provides excellent properties for milk cartons and cold and hot drink cups. However, its use in the microwave oven will be limited to products that will not get hot, such as frozen desserts that may be microwaved to only soften the contents. Similarly, PP coated paperboard is available for microwave only packages in which there is no risk that the hot spots within the package can reach a temperature where the PP softens, causing structural changes in the package or the PP to break down, allowing some of its constituents to enter the food. The dominant ovenable paperboard is PET extrusion coated. With a maximum temperature use of 400 degree Fahrenheit, PET coated paperboard is well suited for forming containers to be used in microwavable containers for a variety of food products. TPX coated paperboard is also preferred in baking applications because of its higher temperature resistance and its release characteristics for sugars that may become caramelized during cooking cycle. And TPX coated paperboard is more expensive than PET coated paperboard. PET-Film-Laminated molded pulp trays are cellulose-based containers most commonly seen as plates and trays. The PET film is required to provide the barrier resistance to fats and oils to go along with the structural characteristics of the lower cost pulp. The cellulose fibers are suspended in a slurry which may contain other components such as sizing and treatment to provide better barrier properties, and pumped to the compression molds, which form the pulp into the desired container shape. The slurry is held into the mold by vacuum, which also draws most of the water out through a screen. Pressure and heat are applied as the mold closes to form the pulp into the container shape and draw out the remaining water. An advantage to this type of molding is the flexibility in the shape of the finished container, which may include divided compartment and areas with varying dimensional thickness for strength. After the molding cycle, the containers are laminated with a cast PET film, which is then trimmed of any excess and packaged. PET laminated molded pulp trays will withstand oven temperatures of 400 degrees Celsius with good stiffness and structural characteristics. CPET or crystallized polyethylene terephthalate. It is a rigid plastic material that can be thermoformed into containers, generally shallow plates and trays. To become microwavable, the PET must be crystallized during the thermoforming process. PET contains nucleating agents that assist in the molecular crystallization. A key factor to consider when thermoforming CPET is the intrinsic viscosity of the material. The amount of crystallization and the intrinsic viscosity will determine the balance between the container stiffness at low and high temperatures. Generally, the crystallinity of the finished container will be 28 to 32% and the intrinsic viscosity will range from 0.8 to 0.95. Prior to extruding, PET must be thoroughly dried to a level of 0.003% to remove inherent water. For thermoforming, great care must be given to temperature control to ensure consistency. The ovens used to heat the sheet on the thermoformer prior to forming must heat the sheet evenly across the dimensions. CPET is considered to be a difficult material to work with because of its toughness and narrow range of operating temperatures. So, proper mold design is a consideration. Generally, aluminum molds are used to promote even thermal conductivity during forming. Often a second stage is used in the molding process is a cooling mold that assists in shortening the cycle time, which helps to stabilize the material after it is formed in the heated mold and makes trimming easier. Because of its toughness, CPET is difficult to trim. The meshed metal dies are used and should be sharpened periodically. Additionally, heavy duty trim presses with quick cycle times should be used. CPET has a temperature resistance of 400 degree Fahrenheit, also has a high gloss, has a hard surface, and can be colored with pigment effectively. Although the preferred colors in the market are black, white, and ivory. PCTA, polymer of cyclohexane dimethanol and terephthalic acid. PCTA is another material in the polyester family that has higher temperature resistance properties than CPET and is a copolyester resin composed of PCTA, which is often referred by estimal company's trade name Thermex. PCTA is a thermoformable material capable of withstanding temperature range between 425 to 450 degree Fahrenheit, and processing is generally considered to be more difficult than CPET because of the higher temperatures required for extrusion and thermoforming and greater cooling requirements. A special nucleating agent is required. However, equipment specified for running CPET will generally be able to run PCTA with the proper adjustments. A PCTA, like CPET, is able to be marked with the Society of the Plastic Industry code as number 1 PET for recycling purposes. Formed CPET. A Cell chemical company has developed a method of making formed CPET that it markets under the trade name PET-Lite. The objective of this material is to produce containers with 35 to 40% less material than conventional CPET. Extrusion equipment used for CPET must be modified for running formed CPET. However, a single screw extruder can also be used. The blowing agent used for the expansion is an inert gas. Generally, processing temperatures for extrusion and thermoforming are comparable with CPET, as are pigmenting and trimming requirements. PET-Lite containers have a temperature resistance of 400 degree Fahrenheit, and currently commercial applications include containers for baked goods such as muffins and cakes. Thermoset polyester. Thermoset polyester plates were the first commercial application of the microwaveable materials when used for frozen meals in the mid 1980s. The compound used is an unsaturated polyester that is highly filled with minerals such as talc and calcium carbonate, along with glass fibers and catalyst materials to produce the chemical reaction to convert the compound into material that is irreversibly set. The polyester compound is mixed and extruded to form logs that are cut to the proper size and weight for the finished container. The material is placed into a heated mold in a hydraulic press that closes the mold. The pressure causes the material to flow into the shape of the mold, and the heat cures the compound while under pressure into the finished and irreversible material. Typically, the container must be sanded to remove any flashing around the edges, and often is run through a conveyor oven for a post-bake cycle to drive off any residual uncured compound and washed to remove any dust from sanding. The process produces containers that are very strong and stiff even at high temperatures of 425 degree Fahrenheit and are heavy with a china-like feel and appearance. Nylon. Mineral-filled nylon or polyamides is a microwavable material that today is no longer commercially available. It is developed by DuPont Canada during the mid 1980s and it is converted by injection molding into containers. Mineral filled nylon plates have a higher temperature resistance and stiffness up to 500 degree Fahrenheit, which is higher than CPET, and were priced between CPET and Thermoset Polyester containers. Although the material was successfully introduced commercially, the use was limited because of higher cost than CPET and also the hygroscopic nature of filled nylon plates, which sometimes caused performance problems in the microwave oven. Nylon has good resistance to oils and fats. However, within the moist operation environment of the microwave oven, some of the water present in the food would be absorbed into the nylon plate, resulting in a loss of dimensional stability. Nylon plate strength was in the conventional oven, where unlike some competitive thermoplastic materials, it retained its rigidity. Nylon plates were injection molded, a process that generally has higher tooling costs and higher operating cost when compared with thermoforming comparable unit volumes. Polyetherimide. Polyetherimide is a high temperature thermoplastic resin which provides a microwavable material for application of about 350 degree Fahrenheit. It is available only in injection molding grades, and with its high price per pound, it is generally better suited for multiple use versus single use applications. It also has good chemical and stain resistance, allowing for it to effectively be cycled through commercial dishwashing systems. Polytherimide has been used for plates and containers in institutional feeding programs and airline meals. Polysulfones. Polysulfones are amorphous thermoplastics which can withstand a temperature of 325 degree Fahrenheit and can be used for microwave purpose. But nowadays it is used for the multi-purpose applications because of its higher cost. That's why single use is not possible. Liquid crystal polymer. Liquid crystal polymers offer very good high temperature resistance of up to 500 degree Fahrenheit in some grades. It can be injection molded and is generally pigmented from its natural beige color. It is transparent to microwave energy. However, the high price of this resin limits its use to specialized applications. Aluminium. Aluminium is capable of withstanding very high temperatures for long times, certainly exceeding the temperature limitations of the food, which was usually available at attractive prices, and could be run at a high speed on packaging equipment. During the early stages of the microwave oven, arcing occurred when metal objects were placed in the oven cavity during operation, sometimes even disabling the unit. This was largely corrected when the electronics were improved so that the energy could not be reflected back into the magnetron. Even though it was safe for the metal objects to be used in the microwave oven, consumers didn't want to take the risk. In the mid 80s, Alco developed plastic coated aluminum tray that was formed without the typical wrinkled corners. The vinyl epoxy coating was often pigmented to appear more like plastic and allowed the tray to work in both conventional and microwave ovens. Performance in the microwave oven is different from that of plastic or cellulose based materials, since the aluminum shields microwave energy, often leading to longer heating times than for similar trays of competitive materials. This lends the design of the tray shape to be shallow to lessen the amount of microwave energy shielded, and coated aluminum foil trays were used commercially for pot pies where they were able to maintain high filling lines speeds. Polycarbonate. Polycarbonate is an amorphous thermoplastic resin that is capable of withstanding temperatures above 400 degrees Fahrenheit. It can be injection molded, blow molded, and thermoformed. Polycarbonate has been used in applications for multiple use products such as microwavable cookware, and it is virtually unbreakable, making it a good replacement for glass. It was used in commercial package during the late 1980s for microwavable meals. The structure used was thermoformed from a 3-layer co-extruded sheet. However, because of its high price per pound, it was replaced by competitive materials that offered acceptable performance for a much lower cost. Polypropylene. During the late 1980s, polypropylene grew as a microwave material because of its flexibility and relatively low cost. Polypropylene use in packaging was bolstered by the rapid growth of shelf-stable mills in which ethyl vinyl alcohol is used to improve the oxygen barrier properties required to safely preserve the cooked food at ambient temperatures. Microwavable containers of PP can be thermoformed or injection molded, generally in two different types, homopolymer PP and random copolymer PP. Homopolymer PP is produced using propylene monomer without the addition of other monomers. Random copolymer PP is similar in polymeric structure of homopolymer PP, but also includes the random addition of ethylene to a propylene chain as it grows. Random copolymer PP gains some molecular orientation, providing certain advantages over homopolymer PP, such as improved impact strength and much better clarity. Homopolymer PP can also be filled with minerals such as talc or calcium carbonate as levels of 20 to 40%. Filled homopolymer PP will have a slightly higher induced temperature and greater stiffness than its unfilled form. A polystyrene by itself does not have a sufficiently high temperature resistance, but when blended with polyphenylene oxide, the temperature resistance property are increased depending on the ratio of polystyrene and polyphenylene oxide. For temperature resistance in the range of 212 to 230 degrees Fahrenheit, a blend of 25% PPO and 75% PS is recommended. PPO has a low resin flow and is therefore difficult to form. However, when it is blended with PS, the flow characteristics and processing requirements are improved. PPO-PS can be thermoformed on equipment used for PS forming with only minor modifications. It is important to have accurate blending during the extrusion process. Therefore, high intensity mixing screw is required. Additional PPO-PS is able to be formed by extruding with tandem extruder systems and blowing agents used for polystyrene such as pentane. HDPE HDPE is an acceptable thermoplastic resin for some microwave applications. HDPE starts to lose its rigidity at temperatures above 200 degrees Fahrenheit, resulting in distortion of the tray or container. So, care must be taken in selecting this material for food products that will not exceed this temperature. This means that foods that have a high fat or oil content or those that generate steam will not be good candidate for HDPE. Generally, applications for HDPE are for foods that do not have a long heating cycle and have a homogeneous texture to balance heating throughout the food, thereby eliminating hot spots. The advantages of HDPE are relatively low cost in comparison with other resins, and processing is and good impact properties at frozen temperatures. HDPE for the food trays is most commonly thermoformed but also can be injection molded. Glass. Although the usage of glass as a packaging material has declined steadily, it is a material that is able to withstand the rigors of microwave heating. Because of the advantages plastic has over glass in consumer safety, transportation cost, and design flexibility, there are very few applications where glass is selected as a packaging material because of its ability to be used in microwave. So friends, in this module we have discussed about different packaging materials which can withstand microwave treatment and can be used as a for microwaveable and irradiated foods.